next this one.
Ma'am, you want to go with the exercise or maybe?
Yeah. You have sent that. You want me to project that?
Yes, I mean,
Or do you have a slide on that? No.
the sample size I have, but
No, today, no, that I have discussed already orally.
okay.
And
Okay.
Dr. Veena, actually, she ran through the example and study design variables. So I think that we are done. You can share today we discussed, no, those examples.
Yeah, so probably I can just copy and paste. I think that should be okay. Should
Yeah,
be
please copy
we
paste.
can, yeah, we can copy
Yeah.
paste that.
Yes. You want me to do?
I
Let
can
me
do
see.
it.
Yeah. If you can, please do that.
All right. So thanks again for joining me. And one of the people say it's a horrible topic, statistics, but it's not horrible actually. But just that you need to uh, think in a layman's perspective, like what is needed for your design. So before I start anything, I just put a question on the chat box. Can you? And basically, this question is like, the title of this question is that two hospitals study HbA1c in diabetic patients and get critical results. Like hospital A, average HbA1c is 6.8%, studied 20 patients, right? That's something you need to remember. So this concept goes back to your sample size again. Hospital B, average HbA1c is 6.8%, same thing, but they studied 400 patients. Okay, so both report the same average. Which hospital result should you trust more and why? Like there are some options given. I'm not going to read those options, but if anybody of you, those who are interested to kind of comment on that, I think you're most welcome.
I think you have a very simple exercise. Yes, please go through the question. Sagarika has mentioned answer C.
Who's
More
saying C?
patient mean average is more reliable estimate of what is true. That is her opinion. Others, please, you can type if you don't want to. Please type your answers. Please come out. Yeah, I know you're in duty rooms. You can still, many of them are doing duties. We can understand their limitations, but still, many have logged in. So, just make a try. Yeah, no more answers. Give a try. Others,
One more minute to go for this
yes.
question. We can, yeah, go ahead. Who is that?
Either type it or unmute and answer. Rita, Richa, Atharva. You have to participate.
All right, I think,
Yes.
ma'am, I think I'll go ahead. So
Yes,
C,
please go ahead.
yeah, I think was given the C. That's a absolutely right answer, because that's how you basically see your the sample selection and the kind of results you are looking at. So C is correct. More patients means average is a more robust estimate of what is truth in the real world. So there are caveats, as I said yesterday, like not too much of sample, but given this the kind of questions I have asked, I think the best answer here is that more patients, more reliable estimate. Okay. So next question is about, okay, I'll just copy and paste again. Okay. So the statement is that if a student says, I stood at OPD entrance in the morning, enrolled first 100 diabetic patients who said yes. Okay. This is the random sampling. So what is wrong with this statement? First of all, do you agree, or do you like, have any other options, ABCD, out of which options you choose?
Please write down your answers. Only Sagarika is attempting. Please attempt. Don't worry whether it's right or wrong. Good. Yes, some more answers, please.
All right. I guess, B is the answer, but at the same time, somebody said D. That's also in a way right answer, because the D is like, you cannot do random sampling with just one group of patients. So B is right, because this is not random sampling. In some way, like it is connected to answer D also, like you cannot do random sampling with just one group of patients. So yeah, so basically those are some kind of, thought provoking questions which I kind of put together here for your benefit. And I'm sure, like, those who have answered, at least attempted, they are in a position to kind of judge these things when you're doing your experiment. So with that, I'm going to switch over to my slides. And let me know if you can see my screen. Can you see my screen?
Yes.
Okay. So this is actually, very interesting module in statistics. So I'm going to go over is something called basic statistics and choice of tests. Okay, and basically the rationale here, or the objective of this session, is that understanding your data before you analyze it. That's very, very important for everybody on this planet who are doing data analysis. Like, you need to understand your data first before you apply any very popular test like t-test or chi-square test. There are so many things, but if you don't understand the data, then there's no point in proposing an analysis and things like that. So that is the kind of objective of this. um, So first is that I think it's already this section is already touch based in the previous topic. Veena ma'am has already touch based, but I'm just giving you a kind of high level overview of the types of data. This is actually considered as a foundation for everything. Like, if you understand this slide very well, probably you are in a better position to handle the analysis part. Or probably there is a chance that if you understand this slide, you can easily conclude that which variable I'm thinking about, which variable I'm dealing about today, and then like what could be the potential statistical test we have to use, I have to use. So you would be in a better position to decide that one. Okay. So There are two types of data. The types of data you basically the type of data you collect determines every statistical decision you make. The entire statistical analysis, t-test, whatever the test, it is based on this table. Okay, so there are two types of tests on a broader level. One is categorical, one is numerical. So under categorical we have three types, and under numerical again we have three types. Okay, so under categorical, you have something called nominal variable or nominal data, you can say. Say, for example, sex, male or female. Okay, that is nominal because you have only, categories, like, or the presence of nephropathy, yes or no kind of thing. Okay, and drug group, dex or fentanyl, so that is actually a kind of nominal variable or nominal data. Ordinal variable, the next one is like, they are kind of ordered categories. Gaps are unequal. Like for example, if you look at the pain scale, okay, severity of pain, okay, basically we have like four categories. One is no pain, mild pain, moderate pain, severe pain. Okay, so basically if you look at your research question, I think there's a research question on DILI severity. So that talks about mild, moderate, and severe DILI, which is like considered as ordinal variable or ordinal data. Why ordinal data? Because there is a inherent order in your data. Like, first is mild, then like increased severity is moderate, further increased severity is severe. That's how the order is happening there within the data. That's why it's called as ordinal scale. Okay. Similarly, if you are looking at the pain scale, the pain score, like 1 to 10 ranked, there is an order, inherent order. Okay, that's the reason it is called as ordinal data. So the name itself suggests you order, ordinal, order. There is an order there. Okay, and the last one is binary here. Only two categories. Yes or no. As I said, like nominal thing. It's here. It is like specific, binary. Only two data points, yes or no. Okay, ATTDILI, yes or no, positive or negative, whether patient cured or not. Okay, only two possibilities here in under binary data. So basically, these things you see it in everyday, day to day life. When you're dealing with the data and patients and things like that. So these are kind of common things. You might have ignored it, but now basically you need to have a conscious effort to see, like, what I'm dealing with, what kind of data I'm dealing with. You can easily make out like what kind of data I'm dealing with. Okay, so those three categories are called categorical data. And next, coming to numerical data, so we have three categories again. One is continuous data, discrete data, or ratio data, or interval data. Okay, so continuous is something like, any number you take, like for example HbA1c in our research question one, which is like, HbA1c percentage, which is like a number. So that's why it is called as continuous scale, because that number, it can take any value on a particular scale. Okay, that's why it is called as continuous. Or say for example serum albumin, so that's a continuous. AIP score, continuous. Anesthesia duration in terms of hours, that's continuous. So any value in a range is, that type of data is called as continuous data. And then comes discrete data, which is nothing but whole numbers. Okay, say for example number of DN complications, number of rescue analgesic doses. Now here the difference here in this category and the previous category is that it's a discrete. You cannot say that 2.1 complications, 2.1 DN complications. You cannot say that 3.1 rescue analgesic doses. That is meaningless. That doesn't make sense. That's the reason. Or for example, number of accident happening in a particular junction, right? That's a whole number there. You cannot say there were 2.6 accidents, right? So that's the reason it is called as discrete data. So that is the major difference between continuous and discrete. Discrete is a kind of whole number. Continuous is that the data can take any values on a particular scale. Okay, then comes the ratio or interval, like for example weight. Okay, and temperature. These are all kind of the ratio or interval data. For example, BMI. BMI is always a ratio. Okay, temperature is a kind of interval. Okay, so that's how it is like viewed as this particular category. So in general, in summary, two types of data on a broader level: categorical, numerical. Categorical, nominal, ordinal, binary, numerical, continuous, discrete, ratio. Okay, so if you can understand this slide very well, then the future slides or the kind of experiment you are going to do yourself is going to be very easy, very easy. So I suggest you that you try to understand this and try to kind of connect these things with your day-to-day uh, mm, exercises which you are doing, or day-to-day lessons you're learning, or day-to-day data or patient data you're seeing, and things like that. So then comes a kind of popular measures here: mean, median, mode. Okay, which tells the truth, right? So mean is basic. Again, I'm not getting into the very detail, the granular details of this, but the mean is the always represented as x bar in a statistical standard statistical framework. So mean is nothing but sum of all values divided by number of values. Very simple formula. Um, Sum of all values divided by number of all values, number of values. Okay, and median is nothing but the middle value when sorted. Okay, so if you have a range of data, so once you sort it in ascending or descending order, okay, the middle value of that data series is always median. Okay, and then mode is like most frequent value. Okay, um, uh, like for example, if you have a series of data, imagine that you have numbers 1 to 10 in a series. Okay, and then imagine that 4 is repeated most of the times, then 4 is your median. So that's how you see it basically. So um, let's look at this example, like HbA1c in type 2 diabetes patients here. Like I put some numbers here, some data here. So patient HbA1 values are like ranging from 6.2 to 14.2. Now the mean value, as I told you, what is the formula here? The formula is that sum of all values. That means like sum of 6.2, 6.8, 7.1, so on and so forth until 14.2, divided by number of patients or the number of subjects or the number of values. So number of values is 10 here if you count this series. Okay, so and then the average is 8.23. So the average mean HbA1c is 8.23 in this series. Now the median is like here is bit bit different here, because the series is a kind of even series. Like there are 10 numbers here. So when you compute the median, we have to take a kind of the uh, fifth and sixth value together, add it and divide it by 2. Because if it is a odd series, then you just pick up the middle value. But here you can't do that. You have to choose a middle two numbers uh, from this series, and they take the average. As simple as that. So what are those two middle numbers here? If you see from left side, 6.2, 6.8, 7.1, 7.3, 7.4, 7.6, 8.0, 8.2, 8.5, and 14.2. So the middle two numbers are 7.4 and 7.6. If you add up them and divide by 2, that is your median. Because why? Because it is a even series. It is not odd series. Imagine that I will remove the last 14.2 value. What could be the median now? The median will be the exact mid value, which is nothing but uh, uh, if you take this series, like the middle value is like I think 7.4. So that's, I think, the middle value if you remove 14.2. So 7.4 is our median during that time. So there are two situations I described you in terms of median. One situation is that if you look at this series, even number of series, like the even number of subjects are there, or even number of values are there. Okay, there are 10 values, patient values here. That's the reason median is always calculated by taking average of two middle HbA1c values. Okay, now imagine that you are removing one observation from here. just as for example, I said like we will remove 14.2. Then you need not take the average, you just pick the middle number here, which is nothing but your 7.4, because that is the exact mid value in this particular series if you remove 14.2. So that's how you see the median HbA1c. Now mode is not, basically I haven't seen using mode in clinical trial or the clinical healthcare research, but probably could be possible that you have to use you know median, sorry, mode at some of the situation. Okay. So now the important aspect from clinical angle is that when one patient has very poor control, like for example, in the series, HbA1c is 14.2%. Okay. That indicates very poor control. The mean is very misleading because mean is always like affected by extreme values. So 14.2, if you see this series, that's a kind of extreme value here. So we always need to check, have some checks and balances in the data also. Like you cannot trust mean always. Okay, you have to go for median in that case, right? So that is something like you need to kind of understand, or maybe like when you put together your when you go to that stage of data analysis, maybe you can connect with me or any statistician on for that purpose. But this is something very important, that between mean and median and mode. Now, this is another kind of property of data, if you like. We always see, we prefer to see the distribution of the data. So we always expect that the data is normally distributed. Normally is a kind of, bell-shaped curve, actually, means like most of the values are like, more or less, they're kind of they're kind of together. There are no extreme values and things like that. So in the previous slide, you have seen, right, there is one extreme value, 14.2, right? But if you see this series remaining values here, 6.8 until 9.5, they are kind of they're kind of together. They're very close to each other. The distance between each value is very less there, actually, compared to 14.2. If you see, there is a huge gap between the rest of the values with 14.2. So that is the kind of thing here. If the values are very close to each other, then obviously we say that the data is normally distributed. That's what our expectation is also, and that is the reason why I told you yesterday that sample size should be kind of minimum 30, because that indicates a kind of normal distribution kind of setup. Okay. So in this case, like when you talk about normal distribution, we always say that it's a kind of bell-shaped curve. Mean equal to median is equal to mode. I mean, that's a kind of one of the properties here. And so, like for example, the series you have, the data series you have seen, HbA1c in a well-controlled diabetic population, that's kind of normally distributed if you exclude 14.2. Similarly, if the data is not normally distributed, we call it as something called skewed distribution. If you see my slide on the upper right corner, skewed distribution, which is not normal distribution, you may observe that the distribution is like more towards right or left side, tail on the right or left side. Okay. And all these properties which I described you, like mean is equal to median is equal to mode, that will fail, that will collapse there. Okay. So basically those are some of the properties of skewed distribution. Now, how do you assess whether your data is normal? Okay, there are four ways of assessing. Again, I'm not getting into the deeper concept of that, but there are four ways of looking at the data. One is histogram, very simple way to see whether your data is normally distributed. There's one more called QQ plot, and there's one more test called Shapiro-Wilk test, and skewness and kurtosis values. In out of these four, I would always suggest you as students, medical students, you use histogram, because when you plot your data in the form of histogram, then you can make out like whether the data is like normally distributed or not. Don't worry too much into that. Even small deviations in your data as a normality is still fine, but as long as you have a kind of bell-shaped curve in the normal data distribution, that's fine. So use histogram, and just use Excel function to draw your histogram. I think anybody can do that. So just use histogram for your purpose to see whether your experimental data is normally distributed or not. So the summary is that we always expect normal distribution in any data. If the data is not normal, that is called a skewed distribution. And like we always have to ensure that any outliers are present in the data, you have to remove them, just like I told you in the previous slide, because 14.2% HbA1c is a kind of extreme value. So in that case, like you cannot reliably trust mean. You have to go for median. So we need to do those kind of permutations and combination when you do the data analysis. Okay, but I'm sure, like when you collect your data, I'm sure, like when you draw the histogram, the data will be normal. Now there are three measures I put here, which is like part of the data analysis. But again, I'm going to touch base it in a very high level, superficial level. So there are three measures here: standard deviation, standard error, and 95% confidence interval. So standard deviation is basically, I told you yesterday also, like this is a very important component of your sample size calculation. So when you see the prevalence rate sample size, for example, you have to look for not prevalence. I think there's one more exercise which I did on sample size where I mentioned about sigma square. If you remember the sample size formula, so that value should get it from literature. So what is the appropriate standard deviation? You have to plug into your sample size calculation. So the standard deviation calculation is basically it is nothing but it describes a kind of variability in your sample. And what is that, like if you see, like if I go back to the previous slide, okay, the data series here, 6.2, 6.8 until 14.2. So okay, now you can make out like what is the variability in this data. Okay, like the distance between 6.2 to 6.8, 6.2 to 7.1, all these things you can make out manually also. You need not calculate the standard deviation. You can make out manually what is the distance between each and every value in this particular data. I think it could be like around point 4 to say point 5 or point 6 or something like that. There is a way to calculate this, but just by looking at this data, you can see that the average standard deviation here is that around say point 6 or point 7 or something like that. That's how you can manually check it. That's not the way, by the way. Don't trust this just because I told you to do this, but sometimes it's very handy that when you see the data, you can easily make out what is the deviation is happening within the data. So that is standard deviation. Now remember that how do you understand standard deviation? Standard deviation can be understood by reversing this word. Okay, now standard deviation is nothing but deviation from standard. I'm just reversing this terminology now, because deviation from standard, the standard is always used as a mean in normal distribution settings. Okay, so if you calculate mean, then what is that deviation is happening from each value in a data series. Let's go back to this example again for your benefit. Um, See this data again. 6.2 until 14.2. Now what is our mean here? Mean is 8.23. Okay. Now what is standard deviation or the deviation from standard? You need to subtract 6.2 minus 8.3, 6.8 minus 8.3, 7.1 minus 8.3, 7.3 minus 8.3, 7.4 minus 8.23, 7.6 minus 8.23, 8.0 minus 8.23, 8.2 minus 8.23, 9.5 minus 8.23, and finally 14.2 minus 8.23. So I'm telling you separately, spelling each and every number, because so that you can understand like how do you see the standard deviation. Okay, so standard deviation is what? It is nothing but deviation from standard. Now what is standard? Standard is mean. So if you look at this particular example, you subtract each value from this series with mean value, and if you do some calculation, the average of all this deviation is called as standard deviation. Okay, so if you see here, this thing here. So example is given here, like we have seen 8.2. I think that's a kind of mean. So standard deviation is 1.4%, which is like calculated. You can calculate using this formula as a homework. Basically, I'm not asking you to do this now, but it's very simple formula actually. Okay, and then comes standard error. So standard error is a kind of way of if you remember yesterday I told you this concept, generalizability. Okay, if your sample is true representation of your population, how do you ensure that you're not committing error in estimating your population parameter. Okay. Now imagine that average or mean HbA1c you got it from sample series is 8.2. Okay. Then you can say that on the average in the population, the average HbA1c is 8.2. Now, how do you precisely know whether it is correct or not? Okay, that is where standard error comes. Okay, now standard error says, if you see this slide, I have given this note there. Standard error says how precisely your sample mean estimates the true population means. That means how what is that error you are committing in extrapolating your sample mean to population mean, or what is that error you are committing while generalizing your sample results to population results. So this is very important measure actually. Standard error, the simple formula for standard error is standard deviation by square root of n. So standard deviation you have already calculated, which is nothing but 1.4 divided by 100. I mean, you can take like whatever the data you get, whatever the sample size you get, but here I took just for illustration purpose, I took 100. So standard error is 0.14%. uh, Now what it says your estimated population mean is plus or minus 0.14% precise. That's how you can interpret this results. Your estimated population mean is plus or minus 0.14% precise. This is what we say, like we always we see, we don't want to be sometimes so we in day to day life we use this example, right? Whenever you say when you express some numbers, okay, when you're talking to your friend and when you're expressing some numbers, anything, any example, like you can say that probably it should be around 10, it could be around 10.2, it could be around 15 or something like that. So you always have that plus or minus kind of things in your language when you talk about numbers always. So this is very important in clinical trial or the healthcare research also, like these two measures. And apart from that, I also have something called 95% confidence interval, which talks about like the range within which you are 95% sure the true population mean falls. So basically, it is nothing but what is that the range of or what you say, how much confident you are about the true population mean. Okay, how much confident. So I'll say that I'll use this formula and say that my mean value is comes under the population mean value comes under, like if you see my example here, like the mean value comes under 7.93% to 8.47%. That is because of the formula used there, like x bar plus or minus 1.96 into SC. Don't worry about the number or the formula here. My intention is not to complicate you here, but the intention is to give you a kind of generic or layman's language or the layman's terms about 95% confidence interval. Okay, so 95% confidence interval is nothing but the range within which you are 95% sure that the true population mean falls. Okay, so in this case, in our example, I calculated HbA1c confidence interval as 7.93% to 8.47%. Okay, so this is a very important measure to kind of when you are generalizing your sample results to population results, you always have to present not only mean but also a confidence interval. Okay, to showcase or to demonstrate that how much confidence we are in generalizing the sample results to population to the entire population. Okay, just remember this, these three important measures. Okay, standard deviation, very much useful for your sample size calculation. Standard error, very much useful. It will tell you how precisely your sample mean estimates to the true population mean, and how precisely you can generalize your sample to population. And then also accompanied by 95% confidence interval, which is nothing but like the range within which you are 95% sure that the true population mean falls. Okay, so that means like you are giving a kind of flexibility there. My true population mean may be between 7.93 to 8.47, even though my mean is 8.2, but still in the population, if you see the population as a whole, the mean could be somewhere between 7.93 to 8.47. So that is the important philosophy behind 95% confidence interval. So in your when you are doing the data analysis in future next year in your experiment, ensure that you present mean as well as 95% confidence interval. Okay, and then comes the hypothesis testing, kind of logic behind that, and this is very important actually. But again, I don't want to complicate you because this is a very difficult, not difficult actually, but it's a very conceptually. You need to be really go deeper into this concept. So there are two kind of hypothesis we are thinking about for any research question. We start with hypothesis basically. Okay, we always start with hypothesis. There are two types of hypothesis. One is null hypothesis, the other one is alternative hypothesis. Okay, what is null hypothesis? Null hypothesis is basically talks about we say that it's always a kind of no difference hypothesis. Okay, if I take your the first research question, the null hypothesis always is that there is absolutely no difference in diabetic nephropathy prevalence rate between controlled and uncontrolled type 2 diabetes patients. That's how I start with. Okay. Whereas alternative is something like you want to prove in using your experiment or using your sample. What is alternative hypothesis? Uncontrolled type 2 diabetes patients have higher prevalence of diabetic nephropathy than controlled patients. So that word higher is very important because that is something you want to prove. What you want to prove is this one. Okay. Whereas null hypothesis, you are not proving anything. First, you are starting with no difference. I say that there is no difference between two entities. Alternative is there is a difference, and I want to prove that uncontrolled T2DM patients have higher prevalence of diabetic nephropathy. So that's how you go ahead with the hypothesis testing. Probably we can discuss about this when you are starting your these thesis writing and things like that. So I think that's the mostly an apt time, I would say, to talk about these things. Okay, and then comes the p-value. P-value is something like a kind of threshold which is already set up in statistical framework. It is that if you get a after doing the data analysis, if you get a p-value less than 0.05%, then we always reject null hypothesis and accept alternative hypothesis. Okay, very simple measure, don't worry too much about that. After you do the data analysis, if your p-value is less than 0.05, then result is unlikely by chance, or rather you say that we reject null hypothesis and we are trying to prove that alternative hypothesis is correct. Now what if the p-value is like greater than 0.5%, sorry, 0.05%? Then we say that alternative hypothesis is wrong, null hypothesis is true. Means like there is no difference between diabetic nephropathy between two groups. So as simple as that one. Okay, and there are two kind of situations here, like we call it as like type 1 and type 2 error and things like that. Okay, so which again I don't want to get into this, but this is something we have already touch based yesterday, that type 1 error or type 2 error, which are like fixed values. Type 1 error always like 0.05%, which you need to input for sample size calculation. Type 2 error is always like 0.2%, you need to input in your sample size calculation. So this particular component I will kind of explain you when you get into that project level mode, the actual data analysis mode. Probably we can discuss that. So until then, I don't want to complicate you many things here. But just remember that when you start experimenting, when you start doing the data analysis, start with null hypothesis, which is nothing but no difference, and alternative, and say that there is a difference. I want to prove that difference. As simple as that one. So choosing the right test, this is a very important thing here. Basically what happens here is that, first you need to understand how many groups are there. Okay. When I say group, means like experimental group, test and reference kind of thing. If there is, if there is, one group, then probably there are different set of tests available. If there are two groups, different set of tests are available. And if there are more than two groups, again, different set of tests are available. So I'll go through this, one by one. Now look at this table, very important table. Okay, this is something like you can always paste it in your at your house, in your room. Basically, this slide as well as the data type slide, which I spoke about at the beginning. Okay, so this is very important. Okay, now let's look at the research question on the left hand side. Okay, compare two independent groups. Okay, DNA in controlled versus uncontrolled type 2 diabetes patient. How many groups are there? There are two groups here. So we have to use independent t-test. Okay, when the data is normal. Remember those things. You need to ensure that your data is normal. Let's hope that data is normal. Then you use independent t-test. Okay, if the data is not normal, for example, then there is separate set of tests available called Mann-Whitney u-test. Okay, and if the outcome is categorical, then we always go with chi-square test. Okay, now compare two paired matched groups like HbA1c before and after treatment. Like one group, I'm saying that, then you have to use pair t-test. And if it is the data is not normal, we have to use Wilcoxon sign rank test. And if the outcome is categorical, then you have to use McNamara test. So on and so forth. So I'm not getting into the details, but for you now, first two lines are very important. Probably I would say first line is very important because in our research questions, most of the research questions, there are two groups already. Okay, so obviously, like you can use independent sample t-test or whichever relevant. If you're going for observational data, of course, odds ratio and stuff like that. But assuming that you're doing a kind of a clinical trial, or if you want to do a independent sample t-test, you can do that one. So first two groups are two sections, or the two lines are very important here from randomized clinical trial perspective. So there is also one more concept called correlation, which is like, again, I'm not going deeper into that. Remember that this slide and previous slide also, something like we can touch base when you actually do the stage of data analysis. Probably I can tell you, like, which is like appropriate test, whether the test coming under this section or is something else we have to use. Is it something like odds ratio you have to use, or is something like other test you have to use? But whatever it is, like, we can decide during that time what test we have to use, or what enhancement we can use. Can we use additionally independent sample t test for any comparison and things like that? So that we can discuss later also. And this is actually a slide talks about the correlation. Correlation is like, if one variable, what is the, what is there any kind of dependency between two variables? So that is the kind of simple definition of correlation. Okay, so there are two types of correlation we are kind of considering. One is Pearson and one is Spearman. Okay, that means, like, again, coming back to the same point here, like, what type of data you're looking at. When both variables are continuous and normally distributed, we use Pearson correlation coefficient. When one when the data is ordinal or skewed continuous data, we use Spearman correlation. Okay, now interpretation of the correlation coefficient is like, the correlation value always takes the value between 0 and 1, not not like, beyond that one. That's how the correlation coefficient is like uh, calculated, or the it's measured. So it's between 0 and 1. So if the correlation is like, say for example, zero point 0 to 0.2, we say that there is no much dependency between two variables. Okay, and if the value is like between 0.2 to 2.4, we say it's a weak correlation. And or something like, zero point 0.6 to zero point 0.8, we say there is a strong correlation. And if the value is 0.8 to 1.0, it's a very strong correlation. Okay, so I did some kind of, what you say, a simple exercise here. uh, the correlation between HbA1c and ACR in your one of the research question, I think the first research question, I got a value as 0.65. So which is nothing but a strong correlation based on that, kind of, the threshold I have put in this particular slide. It comes under 0.6 to 0.8. So I got a value as 0.65, which is a strong correlation. Okay. And there's one more here concept called causation, which again, I don't want to touch base today. But remember that correlation is nothing but, a kind of, it talks about the relationship between two variables, whether they are dependent, whether they're independent, and how much dependent they are. That to see or to understand how much dependent they are, correlation coefficient is used. Okay. So that's something you can easily understand. So yeah, so this is probably this is a kind of a um, exercise I thought. I don't know whether I can copy paste this to. Let me see this. I can copy paste this. Uh,
No, it's okay. I think you can project and they can write the answers in the chat box.
all right. Okay, I'll do
That's
that
all
one.
right, isn't it?
Yeah.
Yeah, you can project. Let them answer in the chat box.
Okay. So let's see this. Okay. So choose the right test. Um, First question is that you want to compare mean HbA1c between controlled versus uncontrolled type 2 diabetes. HbA1c is normally distributed. Which test you have to use? You can put it in the chat box. It's pretty simple because we have already covered this. It's just to kind of revisiting the concept. And the objective of these 4 questions are like, just to make your life simple. Don't worry too much about formulas and things like that. Do you have an answer? Anybody has answer?
Write it out.
Let me see this. Uh,
Yes, Sagarika has answered.
all right. Yes, you're right. Second question. You compare incidence of ATTDILI, yes or no, in malnourished versus well-nourished TB patients. Which test?
Please make it on the full screen, the
Okay.
slide.
Have anybody answered, ma'am? I'm not able to see
No,
the
no,
chat.
no, they have not answered. You're comparing incidence of anti-tuberculous drug-induced uh, liver impairment, drug-induced liver injury. So this question, I think we didn't discuss much in detail. So you have a question where we want to compare whether the question is the incidence of drug-induced liver injury higher in those with malnourishment, BMI less than 18, as compared to well-nourished TB patient. You're comparing these two groups and you want to find out whether it is associated with malnourishment. Which test would you use? So you'll
Yeah. So
compare incidence in this versus other group. Yes, please.
remember that this is a binary data. So I need not tell you, but this is the binary data. I put it in the bracket. So think about it. Which test?
To C. Sagarika has answered as C. What about others? Give a try. She has answered it as ANOVA.
Remember, yes or no answer here. Data is yes or no. Think
Uh,
about it.
compare incidence, huh? Yes or
Incidence.
no? Yes.
What is the
Incidence,
measure?
yes or no? Yes, measure.
The outcome is yes or no here.
Hmm. Means how many yes in this group versus other group? Yes.
I just simply kind of have a data. Yes, no, that's it. I'm not
Yes.
having any values there. So what kind of test?
Try.
Okay. এটা করছিস কাদু?
Nobody is answering. I think you can go ahead. One answer is C. ANOVA. Sagarika has answered as ANOVA. You can go ahead, Dr. Shashidhar. Only one answer we have received. Please unmute, Shashidhar. We are not able to hear you. Dr. Shashidhar, are you there? Maybe he's disconnected. Yeah. We can't hear you, Shashidhar.
Sorry, something
Ah,
happened.
yeah.
Okay,
Yeah, yeah.
let me do
Only
this.
answer given is C. 2 is C.
C.
Answer given. Mm.
Okay, okay, fine. Yeah, that's fine. I think. Yeah. Maybe I can go to fourth question.
Yeah.
You want to see AIP predicts
Are we
diabetic
using ANOVA in this question number 2? Yes
No,
or
we are
no?
not using ANOVA
Ah, you're
because
not using, no?
remember, I didn't
Yes.
touch base ANOVA at all because
That's
ANOVA
all.
is a bit more complicated.
Yeah.
So if you have more than two treatment groups, then we go for ANOVA. But none of the
Yes.
research questions we have more than
Correct.
two treatment groups.
Yeah.
In general, I'm saying, you may
Correct.
adopt
Correct.
some other, maybe case control or the odds ratio kind of setup. But if you see it as a clinical trial, there are not more than two groups. So ANOVA is not applicable, which that's the reason I didn't tell about ANOVA.
Correct.
Um,
Correct.
so obviously, like answer B is something important here.
Correct.
Chi-square test for question
Correct.
number 2. Remember, yes, no kind of answer here. Okay.
Mm.
So question number 4, you want to see if AIP predicts diabetic nephropathy after adjusting for age and HbA1c, which method? Okay, I didn't touch base this, but those who are
Correct.
interested, you can answer this question. I didn't touch base, by the way. I remember that I didn't talk about this one, this particular thing.
Yes. Anybody
But
would like to attempt?
yeah, if you want to attempt, more than welcome.
No. Yeah.
It's bit not so easy, but
You can go
if
ahead.
you
Yeah. You can
yeah,
only cover. Nobody has answered. You can go ahead.
nobody. Okay, so this is basically logistic regression, which I didn't cover because the outcome measure is yes or no kind of thing, but it says like the question says after adjusting for age and HbA1c. So basically, this talks about some sort of statistical modeling here, which I didn't cover. So logistic regression is the appropriate test here. Okay. So, but thanks for answering these things. So
Answer
let's
C. Yes.
do.
Sagarika has answered C. Correct. Yeah. She has
Okay.
answered now. Yeah. Okay. Please go ahead. Yeah.
Yeah. So everything is here. So I
Yes.
answers are here. So when you get the slides, obviously you can see the answers here.
Correct.
Um, so now, I mean, again, you can go through this. I need not because in some way these are already covered in the previous session. So you can just go through this. I just put together as a kind of as a framework to kind of understand like what exactly I covered in the previous slides. Okay. So this is also like common statistical mistakes, what examiners are looking for when you are doing this, when you're talking to your guide, what they are looking for. That's something you need to understand. Like for example, using t-test for skewed data, not recommended. You have to check normality first. If the data is skewed, then go for Mann-Whitney U-test. Reporting only p-value without effect sizes, confidence interval. That's something a mistake you are doing. So always report whatever the measures like odds ratio, relative risk, or mean. Along with that, you have to report 95% confidence interval. Okay, and then there are other things which I again don't want to cover here, which are like complicated for you now for this time, and then confusing between statistical significance with clinical significance. Okay, like for example, a tiny HbA1c difference of 0.1% may be statistically significant, but in 1,000 patients, but it's not clinically, it's kind of clinically meaningless. So these are some of the points I just wanted to highlight here from stats angle, but last 2 points probably may not be required for you, but it's good to know, for your understanding. So I think, yeah, so key takeaways, first is know your data very well. Okay, the first slide, remember first slide, categorical. If the data is categorical, go for chi-square test, logistic regression. If the data is continuous, go for t-test, Mann-Whitney if it is skewed. and identify that before anything else, before anything else. Always check normality. Another thumb rule. Plot a histogram. I told you already, which is very simple for you. And other things you can ignore. Like I would suggest you to plot a histogram, and then report beyond p-values. Just note, don't just present p-value. Just along with that, you put, display confidence intervals also. Match your test to research question. Okay, use flowchart if at all possible, and then you can easily map out like what kind of data you're using, and what kind of test and what kind of results you want to display. Okay, and the correlation concept, which already told you, and causation, just simply ignore for now. Causation, I don't want to again confuse you. Correlation is something like, which talks about like how two variables are associated with each other. So those are the kind of key takeaways for today. And probably in future, when you start doing sort of data analysis and things like that, more than happy to support you in that case. I think that's it from my end, everybody. And if you have any questions, you can ask me now. Or if you don't have any questions, that's fine. You can drop me an email or something like that.
Any questions, you can put it in chat box also now. We can take one or two questions.
Yeah, you can do that. Yes.
But good, nice presentation, Shashidhar, as always. And I have liked the way you put in a crisp and very brief 1 hour. You told very interesting and useful points. And I'm sure that's how some people have also attempted. More could have attempted the answers, but maybe they'll go through the slides and recordings, and then they'll come back again. Very good. As always, as I said, very interesting presentation of statistics. Whatever is required, that much only he will convey. And that's what I like about his presentation. Any questions from students?
So one last thing I want to mention here, that
Please.
don't let what you say, like there are some formulas in this presentation, but don't let yourself that, oh, there are formulas, I don't think I can. So that is not the way. Just look at the simple things. I think start from there. Don't worry too much about formulas. Formulas are there because formulas need to be there for computation purpose. But understanding the philosophy is something very important. That will determine your, kind of, the way you are dealing with the, experiment and things like that. So don't worry too much about formula, but worry about philosophy concepts.
Yes. So your discussion with the statistician will be very effective when you have very clear research question, objectives in mind, and you go with thorough literature research, literature review, and carry some good recent published articles which are relevant to your objectives. The reference articles should be related to your objectives. So if you go with those supporting data and your objectives, where if you're very clear about what you want, then statistician will be very then you discuss with him for sample size, sampling, statistical tests. That will make it more meaningful. But you must have this background information also. You cannot tell just like using AI, just give some command and then it gives whatever it gives. If you accept, that's not done. Even the biostatistician would like to know what is in your mind, what are your objectives. So it is a combined teamwork. It is your effort, your preparation with biostatistician. He will not be able to decide clinically what is relevant to you. He will only tell you which test and what sample size, what design is most appropriate to arrive at, to prove the or disprove your hypothesis. So your preparation, even when you go to statistician, is extremely important. Right? Okay. So if there are no questions, with that, we conclude today's session. And I'm happy we had Dr. Sumana and Dr. Sushma also who had joined the session. Dr. Sushma Naidu is Professor of Pharmacology in PES, and she will be your faculty tomorrow. Dr. Sumana is Pathology HOD at Manipal Hospital, and she will be chairing the session on Saturday. She has been my good friend. And Sumana, hello, good evening, if you are there, or if you are there. And she will be, she is an expert in many things. I will introduce her to you all on Saturday. She does complex histopathological diagnosis, some of the rarest in the country. And also she has worked in Boston University. So good that she has joined today. And Sumana, are you there? So with that, I think we might conclude today's session unless you have any queries, participants. All right. Thank you. Thank you so much, all of you. Great to see your efforts. When I spoke to you all, I understood the interest you have. Today, I had a chat with some of you on the phone. Tomorrow, again, I will speak to some of you. I'm happy to learn that you are going through the session, the PowerPoint presentations and the recordings. So please send your email, or I think we have it in your Google Forms. We will share all the recordings to you, but by Saturday, if you can come out with your some proposal, brief, not in detail, a summary of your synopsis, I should say, then we would be more than happy to discuss. Take up 3 or 4 of them so that it will help you to design your synopsis. Thank you. Have a nice uh, evening. That's all. Thank you so much.
Thank you.
Thanks, Dr. Shashidhar. Thank you once again.
Thanks a lot.